Hello, I'm Rohan and along with Nitin giving a presentation on solar powered golf cart for St. John's. The objective is to design and simulate battery powered golf cart that can be intermittently charged using solar energy resources available in St. John's. These are the steps taken to achieve our objective. First is system design, where we look at the electrical circuit required to charge the battery via solar panel. Then comes system sizing, where the rating and size of different components are selected based on power requirements and size limitations. Third comes system control, where an algorithm is implemented to solar resource to max potential, after which the complete design is simulated in Simulink for analysis.
Hi everyone, I am Nitin. The working of a solar power golf cart can be explained with the help of the block diagram as per figure 2. Here we can see the systems that are involved in the operation of a solar powered golf cart. The system consists of a vehicle body for two occupants which is powered by a 3 horsepower or 2.2 kilowatt permanent magnet DC motor via transmission gear. To help control the output of the DC motor and thereby the speed of the vehicle body, the input of the DC motor is connected to the drive controller with the help of a power converter. The power converter also helps in transferring power from the battery, which is charged from the solar panels on top of the canopy of the golf cart, into the DC motor. A drive cycle is set up so that we can increase and decrease the speed to analyze the output parameters of the vehicle body of a solar powered golf cart. The vehicle body, as shown in figure 2, is used to input various parameters like body mass, aerodynamic drag, road incline, and weight distribution between axles due to acceleration and road profile. Connection H in the mechanical translation serving port associated with the horizontal motion of the vehicle body. The resulting traction developed by tires is connected to this port. Connections V, NF, and NR are physical signal output ports for vehicle velocity and front and rear normal wheel forces. The resultant velocity of the vehicle can be measured with the help of vehicle body systems. The tires, which are connected to the vehicle body, are used to input different set of parameters like rolling resistance, rolling radius, and a few more to the vehicle body system. A 48 volt 3 horsepower or 2.2 kilowatt permanent magnet DC motor, as shown in figure 4, is used to power the golf cart. A permanent magnet DC motor is a type of DC motor that uses a permanent magnet to create the magnetic field required for its operation. The permanent magnet DC motor is connected to the vehicle body with the help of transmission gear system for forward and reverse motion. They help in analysis of various parameters like armature inductance, no load speed at rated load, rated electrical load, rated DC supply voltage, rotor damping, and no load current, along with mechanical parameters like rotor inertia and initial rotor speed can be set with the help of DC motor block.
To determine the feasibility of independently and autonomously powering the golf cart with sunlight for use in St. John's, we'll first look at the power requirements and equipment needed to power the golf cart from solar panels placed on top of the canopy cart. The amount of energy an electric vehicle requires depends on certain variables like the type of golf cart that is to be used, the size of the canopy, how much range is required from the golf cart and the components, and the battery system that is to be incorporated into the golf cart. The number of solar panels and their area depends on the range required for the golf cart and the battery size. For the system, we are using a golf cart having a DC motor with a rating of 2.2 kilowatt and a maximum speed of 31 kilometers per hour, where it attains 0 to 30 in 5 seconds. These are the basic hand calculations done to give us a minimum estimate of requirements, as real-world applications would differ based on various factors like friction, weather, weight, etc. For the selected site, the clearness index is between 0.39 to 0.49 with an average of 0.44 and solar insolation varying between 1.28 kilowatt-hour per meter square per day to 5.14 kilowatt-hour per meter square per day, with an average of 3.15 kilowatt-hour per meter square per day. The figure illustrates the solar radiation and clearness index for the selected site in St. Johns, Newfoundland, Canada. The circuit scheme of MPPT controller is shown in figure, which consists of Vs as a photovoltaic voltage source, inductor L, diode D, capacitor C, MOSFET as a fast switch, and load, in this case a chargeable battery. The switch S of MOSFET in circuit of MPPT is connected with PWM, which results in duty cycle from P&O algorithm. Maximum power point tracking is an algorithm implemented in photovoltaic inverters to continuously adjust the impedance seen by the solar array to keep the PV system operating at or close to the peak power point of the PV panel under varying conditions like changing solar irradiance, temperature, and load. Engineers developing solar inverters implement MPPT algorithms to maximize the power generated by PV systems. The algorithms control the voltage to ensure that the system operates at maximum power point or peak voltage on the power voltage curve. MPPT algorithms are typically used in the controller designs for PV systems. The algorithms account for factors such as variable irradiance, that is sunlight, and temperature to ensure that the PV system generates maximum power at all times. The algorithm perturbs the operating voltage to ensure maximum power. While there are several advanced and more optimized variants of this algorithm, a basic P&O MPPT algorithm is shown below.
The speed of the solar power golf cart is controlled with the help of a longitudinal driver block as well as the use of H-bridge converter. The longitudinal block is a proportional integral controller which takes feedback with respect to the vehicle velocity and then compares it with the input velocity that allows the longitudinal speed tracking controller for generating normalized acceleration and braking commands. The output of the longitudinal driver is forwarded to the DC motor in order to control the speed of the vehicle with the help of an H-bridge converter. The H-bridge converter is a DC to DC converter, basically which consists of a combination of 4 electronic switches which controls the voltage of the DC motor. Here we can see the entire MATLAB SIMULINK model for the solar powered golf cart. On inputting the values of irradiance and temperature to the solar panel of around 1000 watt per meter square and input temperature of 25 degrees Celsius in order to operate the solar panel with the help of perturb and observe maximum power point tracking method, where the power from the solar panel is maximized for a particular set of voltage using this maximum power point technique for a particular irradiance and temperature condition. The output of the solar panel is connected to a boost converter which boosts the output voltage and charges the battery. The battery then powers the permanent magnet DC motor of the golf cart, making it ready for its application. A much simpler MATLAB SIMULINK model for the same system can be shown in the next slide. As the battery of the solar powered golf cart is charged to around 90% of its state of charge with the help of maximum power point tracking method, that is perturb and observe method of maximum power point tracking, the battery is further discharged to power the DC motor. As a controlled voltage is provided from the longitudinal driver through the H-bridge to the DC motor. To obtain the desired output speed of the vehicle body, an input velocity is provided to the longitudinal driver setup to get the desired output speed. The input velocity provided by the user is then compared with the feedback velocity that is obtained from the vehicle body inside the longitudinal driver setup, which is basically a PI controller block that compares the input speed value with the speed obtained as a feedback from the vehicle. If the input value is greater, the acceleration command is forwarded through the H-bridge through the controlled PWM voltage block, thereby increasing the power of the DC motor from the battery, and braking occurs for lower input speed when compared to the feedback speed provided from the vehicle body. If the input speed is greater than the feedback speed, an acceleration command is passed on from the longitudinal driver block. The acceleration command is passed on in the form of voltage and current signals into a constant controlled voltage source and a controlled current source. The output from the controlled voltage source is fed into the PWM voltage block, which is then further passed on to the H-bridge converter. The output PWM signal from the PWM voltage block is then compared with the reference signal that is obtained from the DC motor in order to decide the amount of power that is needed to be dissipated from the battery to the DC motor. Then the DC motor accelerates or decelerates proportionally based on the set power from the battery. The power from the DC motor is passed on to the vehicle body with the help of transmission gears, which are connected to the axles of the vehicle body of the solar powered golf cart. Thus, an output velocity that closely matches to the input velocity that is provided by the user is achieved in a certain amount of time for the solar powered golf cart. On analysis of the simulation of the MATLAB model for the solar powered golf cart, it can be observed that for changing the input velocity of the longitudinal driver, you can see that the output speed of the vehicle body matches with the input speed in a matter of seconds. We can see from figure 13 and figure 14, which is the relationship between distance and time and velocity and time of the solar powered golf cart to be linear in nature. Some of the drawbacks that can be seen in the application of solar powered golf cart would be that the solar powered golf cart are very small in size, thereby only allowing less amount of energy storage inside the cart. And the solar panels that generate energy require much more space than the golf cart canopy can provide in order to house the solar panels. Hence, solar panels with high energy to surface area are required for such operations. This brings us to the end of our presentation. Thank you.